Hello everyone. um, so this is my folder and welcome to this video where I'll talk about the introduction to the pipelining. So let's get started. Now what is pipelining? Now here in this slide I have already shown that like an automobile assembly line for instructions, each step does a little job of processing the instruction. Ideally each step operates in parallel. Now this I've given an example to specify this in the computer architecture language. I can say, you suppose you have been given a process and you have to operate it and compute it. Now what a machine will do is that with each process it will divide into their sub processes being executed in a partial dedicated segment that operates concurrently with all other segments. Okay, now this is pipelining. Now the third point is given that pipeline can be visualized as a collection of processing segments through which binary information flows. Obviously yes, the pipelining is nothing but a segmental concurrently operating processes through which the binary data can flow. So now we come to the second slide. Now there are two types of pipelines. For example, the number one is arithmetic pipelining and the number two is instruction pipeline, which is this one. So at first let me discuss about the arithmetic pipeline organization. Now suppose for example the arithmetic logical unit of a computer operates with the addition, multiplication, subtraction and division. Now here for a given example I have taken a into b plus c. Okay, now there's a memory which will store all the values of the a, b and c. Now what the segment 1, that means this segment will do is that in the register 1 the value of a will be stored and the register 2 the value of b will be stored. Exactly after that the multiplier logical unit will multiply the values which were stored in r1 and r2, that is a into b, and that value will be stored in the register 3, which is also known as segment 2. Now what will happen in segment 3 is that from r3 the value and directly the value of c will get stored in r4, and concurrently the adder unit will add these two values and store the value in r5. So we are seeing that a particular single process, that is a into b plus c, is divided into segment 1, segment 2 and segment 3, which are operating concurrently with each other, and the final value is getting stored at r5. Now the instruction pipelining. Now this is a common concept of any pipelining execution, is that first the instruction gets fetched, then it gets decoded. If there is any branch, then it will directly update the program counter which stores the address of the next instruction, and if there is no branching, then the operand will be fetched from the memory and the execution of the instruction will take place. Now if there is no interrupt, then directly the instruction gets fetched from the memory again and the cycle goes on, and if there is again an interrupt, then the interrupt handling is done, the program counter is updated where the address of the next instruction is get, and then the pipe is get emptied, and then again the cycle goes on and fetching, decoding and execution takes place. Now with the example of the arithmetic pipelining, here we are showing a small operation in each pipeline stage. What happens is that with each we have made here 4 columns: clock pulse number, segment 1, segment 2, segment 3. This was the segment 1, segment 2, then segment 3. Now how we can show theoretically that pipelined process are way more faster than a single process which can occur at a time. Okay, now dividing a single process into 3 subsequent processes which occurs and operate and gets computed concurrently, they are way more faster than a single process which gets operated and computed in a single time. Okay, now here the clock pulse numbers are from 1 to 9. We are seeing that how this process gets computed in 9 clock cycles is that in segment 1 the value of a1 and b1 till a7 and b7 gets stored in the registers. We have seen here in segment 1 the value of a is stored in r1 and value of b is stored in r2. Okay, now in segment 2 in register r3 and in register r4 respectively, a1 into b1 the value is stored in r3 and the values of c's are stored in r4. So we have seen here the value of a and b after getting multiplied is stored in r3 and value of c is stored in r4. Now in segment 3 the exact calculated value of A1 into B1 plus C1 till A7 into B7 plus C7 is getting stored in register R5. So in clock pulse 1 till clock pulse 7, the storing of R1 and R2 values is getting done. From clock pulse 2 to clock pulse 8, the multiplied values of A1 to B1 is stored in R3 and the values of C1 is stored in R4. And till clock pulse from 3 to clock pulse 9, the exact values after the calculation is being stored in R5. So this is how a pipeline operation takes place at each stage for a given clock cycles. Now this is the continuation of the previous slide. Pipelining requires buffers. Obviously, if any subsequent processes are getting occurred and computed, for example here the instruction is getting fetched, then the instruction is getting decoded. So in between, obviously there is a data flow, and for a data flow obviously there should be a buffers. Now what is a buffer? Buffer is a short temporary storage which stores a normal data or a short data or a binary data where a data flows takes place between two places or between two memories, for example instruction fetch and instruction decode. So here we are seeing B1, B2, B3 and B4 are the 4 buffers which are required between the 5 blocks: instruction fetch, instruction decode, operand fetch, instruction execution, result write back. Each buffer holds a single value. Yes, it's given. Ideal scenario, equal work for each stage. Sometimes it is not possible. Slowest stage determines the flow rate in the entire pipeline. Now the next slide. Yes, operand fetch of I2 takes 3 cycles. Yes, obviously in clock cycle till 1 to 10, and here we are taking instructions I1 to I4. IF is the instruction fetch, ID is the instruction decode, OF is the operand fetch, I is the instruction execution, WB is the write back. Now just see from clock cycle 4 to 6. Okay, I, E, W, B and the other blank block is getting executed by operand fetch, which is taking 3 cycles. Now what is happening is that here pipeline stalls are taken for the 2 cycles. This is nothing but a pipeline hazard which we will discuss in the upcoming slides shortly, and pipeline stalls reduce overall throughput. Obviously if there are no stalls and if hazards are taking place, then these hazards are making pipeline process slower. So we introduce stalls so that we can overcome the hazards and make our process work faster. Yes, now the major hazards in the pipeline execution. Obviously if any execution, any process or any operation is getting executed or computed, there must be some hazards while computing. So there are 3 major hazards, which are structural hazards, data hazards and control hazards. Structural hazards we will be discussing at first, which is also known as resource conflicts. The hardware resources required by the instructions, simultaneous overlapped execution cannot be met. Data hazard, secondly data dependency conflicts. For example, at a particular clock cycle, suppose if one memory is getting dependent on the another memory, but the first memory is not getting freed up, so that data gets dependent on the next cycle. So here the conflicts takes place and the hazards occurs. So we have to overcome this by the process of forwarding, which we'll be discussing in the upcoming slide. And the last but not the least is the control hazards, which is also known as branch difficulties and branches and the other instructions that changes the PC, that is program counter, which is nothing that stores the address of the next instruction, make the fetch of the next instruction to be delayed. Next slide we are discussing the structural hazards. Consider a CPU with a single memory pipeline for data and instructions. Now if an instruction contains a data memory reference, which I will be showing in the next slide, okay, so it will conflict with the instruction fetch. Obviously yes. Now please concentrate on this slide. In the loading process there's 5 blocks: memory, register, arithmetic logical unit, memory and register, from clock cycle 1 to clock cycle 5. Fine. Now the instruction 1, what it will do, the instruction gets operated and computed from clock cycle 2, obviously yes. So memory and register, the memory gets the value from the register, the second register gets the value from the ALU, the third ALU gets the value from the memory, and then again the memory gets value from the register, and so on the process takes place. Instruction 2 concurrently they are getting computed. Now what the problem that we'll face is in instruction 3 at clock cycle 4. Just see there, the memory in the load portion, it is again needed in the instruction 3 at clock cycle 4. So here what the conflicts is taking place according to the structural hazard is that at the same clock cycle the structural hazard is taking place. Okay, Now what happens is that instruction contains a data memory reference and the instruction fetch conflicts takes place. Okay, now how to overcome this? A very easier process. Nothing, we have to introduce stalls or bubbles. Here no execution or computation takes place. So what will happen is that in instruction 3 the memory gets overlapped to the next clock cycle, that is clock cycle 5, and the conflicts does not takes place. Alternate depiction of stall, this is another way of describing it or showing it. Now avoiding the structural hazards. So there are many ways. The one of the important way I have already discussed, that is the stalling process to introduce stalls or bubbles. Now how can we avoid structural hazards is that issue of cost for the designer. Example, allow multiple access paths to memory, separate access to instructions from data, separate data instruction caches, build multiple ALU or other functional units. Don't forget the cost performance trade-off and Amdahl's law. This is the most important trade-off which is often discussed while avoiding the structural hazards. We avoid the expense to design hardware to address it, instead just handle it with a stall or other method. Now data hazards. Data hazards generally occurs when the pipeline changes the order of the read-write accesses to the operands that differs from the normal sequential order. For example, a short example has been given here. Add R1, R2 and R3, there are 3 registers, fine. Then sub R4, R1, R5 and operation at RC, R1, R7 and OR operation at R8, R1, R9 and XOR operation R10, R1, R11. So what's the problem here? Just see here, while adding R2 plus R3 and storing it at R1, okay fine, we have done, but when we are needing this R1 register in subtraction operation, this R1 is not freed. So here the conflicts takes place and the data hazards we are experiencing. So how to overcome this? So this is the representation of the data hazard. See here, CC5 at clock cycle 5 this register is needed by register, second register in at clock cycle 3, in clock cycle 4 and in clock cycle 5 and in clock cycle 6. How to overcome this? By forwarding. This is a technique to minimize data stalls, as in the previous example. Now we have actually computed the correct result needed by the other instructions. But it's an earlier stage. What we'll do is that we'll just swap two places. For example, in the place of sub R4 R1 5 we'll put and R6 R1 R7. Okay, so what will happen is that we'll forward this data to the subsequent stages where it may be needed. ALU result automatically fed back to input latch for the next stage. Need control logic to detect if the feedback should be selected or normal input operands. So this is the representation of the forwarding techniques. You can see here, this buffer is forwarding the data to this ALU, this buffer is forwarding the data to this ALU, and in the final register where the value gets stored is used up by this register. So see, after getting forwarded we are not getting any data hazard. So this was the solution of the data hazard. Scoreboarding is one of the another way to implement the control needed for forwarding. Scoreboard stores the state of the pipeline. Well, in our syllabus scoreboarding is not so important, so I'm not focusing on this topic. I'm just reading out this slide, what stage each instruction is in, status of each destination register, source register, can determine if there is a hazard and know which stage needs to forward it to what other stage, controls via multiplexer selection. If state of the pipeline is incomplete, stalls and get pipeline bubbles. Obviously in scoreboarding, if any of the hazard we are facing, stalls are the minimum and the most common way of overcoming the pipelining hazards. The most important topic rather than the types of data hazard classification is that we have 3 types of data hazards. Okay, now suppose there are 2 instructions. Okay, instruction I comes before instruction J. Okay, now the 3 types of data hazards are RAW, raw, read after write, WAW, write after write, and WAR, write after read. What happens in RAW, read after write? Suppose first of all, the given instruction, the given data is very important, that is instruction I comes before instruction J. Okay, now J tries to read a source before I writes it. Obviously if J will try to read a source before I writes it, so J incorrectly gets the old value. So this is one of the hazards. So in the resulting register the wrong value gets stored, and we get the wrong value. So this is one of the major data hazard, and this can be solved obviously via forwarding, because last example which we discussed was nothing but read after write data hazard. Now secondly, WAW, that is write after write. J tries to write an operand before it is written by I. Obviously the previous example, actually in the previous example, all of the three important data hazards is being discussed. Read after write, WAW, write after write, is that suppose after the adding operation which was in R1, R2 and R3, in the subtraction operation, obviously in R1 we have to write the values and get stored the values of R4 minus R3. So what will happen is that if J will try to write an operand before it is written by I, suppose instead of subtraction the multiplication operand is being updated there, so obviously we end up writing values in the wrong order, so we'll get the wrong value, and this is one of the data hazard which is nothing but write after write. So RAW can be solved via forwarding. And yes, WAR, that is write after read. J tries to write a destination before it is read by I, so I incorrectly gets the new value. For this to happen, we need a pipeline that writes results immediately in the pipeline, and another instruction reader source later in the pipeline. Okay, now the last but not the least is the control hazards. Now control hazards are nothing but the hazards which is caused due to branching. Control hazards result when we branch to a new location in the program, invalidated everything we have loaded in our pipeline, potentially a greater performance loss than data hazards. So this is one of the important point. Which of the three hazards in the pipelining causes the greatest performance loss? So this is nothing but the control hazards. Simplest solution is stall until we know the branch. Obviously stall, as I already said, yes, potentially a greater performance loss than data hazard. Simplest solution is that stall. So as I said, stall is the most common way to overcome any hazard in pipeline. Actually a 3-cycle stall, since we may need a new IF. Now this is the short example of the control hazard. Yeah, so here's it. Thanks, and we end up this video.